Hi, I'm Dr. Courtney with the Quantitative Reasoning Center. And you probably have realized by now, since you've probably had an opportunity to pick partners and work in groups for several student projects, that there's two kinds of people. There are those who are pretty good at finding excuses for substandard outcomes. And then there's the other kind of person who's very good at always finding a way to get the job done, finding a way to succeed regardless of what challenges or impediments might come along during the process. So while this is an important skill to have, recognize what kind of people you're dealing with when picking partners for a group or team members. It's much more important to make the choice, what kind of person am I going to be? Am I going to be a person who is skilled at finding a really good excuse why the task didn't get completed? Or am I going to be the kind of person who finds a way to succeed? Today, we're having a look at 16.3, number 17, and we're given a vector function, where this is the x component, the y component, and the z component, and we're given a space curve, r, with an x, a y, and a z component as well, which is the path through space from t equals 0 to t equals pi. And the task is to find f, which is a scalar function, such that the vector function is equal to the gradient of that scalar function, and use the scalar function to evaluate the integral of f dot dr over the path. Alright, so what's the big idea here? I mean, we might be tempted to proceed in the way that we have in recent work by expressing everything in terms of t, parameterizing it, simplifying the integral into an integral over time, and using a computer algebra system to evaluate that integral. Taking that approach would be a useful assessment method, and we should get the same answer as actually solving the problem according to the instructions. But the instructions basically are leading us down the path. So to interpret this problem, we're going to use the fundamental theorem of line integrals to find the integral of f dot dr over the contour C. In other words, what the fundamental theorem of line integrals does is it gives us a tool to evaluate an integral without actually working the integral. So that's actually how we interpret this correctly. So to develop our plan, first we need to think about how are we going to find f such that the gradient of this scalar function f is equal to the vector function. So both of these are functions of position. In other words, we could write in the argument list x, y, and z because they're both three-dimensional functions. Lowercase f is a three-dimensional scalar function, or a scalar function of three input variables. The uppercase f with the little vector arrow on top is a vector function of three input variables, x, y, and z. Alright, and how do you do this? Well, you do it term by term. And then you summarize. Once we have the scalar function, then we use the fundamental theorem of line integrals directly. And there's some mechanics here, some sub-steps. In other words, we want to evaluate, so we need to find the vector r at t1 and the vector r at t2, and then we substitute in to the fundamental theorem of line integrals. Alright, well let's go ahead and go down this road a little bit. So what does it mean that the gradient of the scalar function f is equal to the vector function? Well, keep in mind that a vector equation in 3 dimensions is really 3 scalar equations. So what this means is the partial of f with respect to x is equal to the x component of this vector field. So it's y squared cosine z. So what does this tell us about the scalar function f? Well, it tells us that f, and if you just integrated this with respect to x, right, f has to be equal to x y squared cosine z plus some function, and I'm going to call it c sub x because it's constant with respect to x, but it can be a function of y and z. So if you differentiate this, take the partial derivative of this with respect to x, this is just a function of y and z. Its partial derivative with respect to x is 0. The partial derivative of this with respect to x gives you back the x component of the vector function. Alright, partial f, partial y, now thinking about the y component of the gradient, has to be equal to the y component of the vector field. So what does that tell us about the function f? Well, if we integrate this with respect to y, or over y, what we would get is x y squared, because the integral of y is y squared over 2, the 2 in the denominator cancels out, times cosine z, plus now a constant with respect to y, but it can be a function of x and z. And you can see if you differentiate this with respect to y, this term will give you 0 because it's only a function of x and z. Partial derivative with respect to y is 0. And the partial derivative of this with respect to y is going to be 2xy cosine z. So our double check works. Partial f, partial z is the z component of the gradient, and that must be equal to minus x y squared sine of z. And if you think about it, integrating with respect to z, or integrating over z, it's going to be x y squared cosine z plus some constant with respect to z, but it can be a function of x and y. So in this case, we don't have any terms to combine. Sometimes we do. The function f is simply xy squared cosine z plus perhaps a constant, but it's something that would be a constant with respect to all the variables in the problem. So our function f we can take as simply xy squared cosine z. Alright, so now how do we use this? How do we bring the fundamental theorem of line integrals to bear on our problem? Well, the basic idea of the fundamental theorem of line integrals is that if you have a function f that's the gradient of some scalar, then you integrate it over a curve with respect to dr, then it turns out to be f of r of b minus f of r of a. And we need to take some care because this r of b and r of a are really the initial and final points along our curve. In other words, to actually apply this, r of b is equal to r of pi, because the integral goes from t equals 0 to t equals pi. And so r of pi, well, what's r of pi? R is the point in space where the curve is at t equals pi. So r of pi is equal to pi squared sine pi and pi. All right. What's r of 0? Well, 0, sine of 0, and 0. So the integral of interest we have to evaluate the function x y squared cosine z. First we evaluate it at this point in space, which is pi squared. What's sine of pi? Well, sine of pi is 0. And what's cosine of pi? Well, cosine of pi is 1, but since we're multiplying by the 0 here, it's equal to 0. And now we have to subtract f at this point. Well, this is just f at 0. X is equal to 0, y is equal to 0, z is equal to 0. So this is 0. So the integral works out to be 0.